Have you ever been on a plane and just wondered what keeps this massive, incredibly complex machine safe flight after flight, year after year? It's not just about how it's designed, it's really about this hidden world of constant vigilance. So today, we're going to dive into one of these invisible guardians. We're going to decode a real, official safety mandate to see exactly how the system works. And that's really the key question, right? A plane rolls off the assembly line, shiny and new, but its safety journey has only just begun. The real work is this continuous process of monitoring, detecting, and fixing potential issues long before they can ever become actual problems. And the main tool for that? It's something called an Airworthiness Directive. Okay, so the easiest way to think about this is it's just like a car recall but for aviation. When a safety agency like EASA over in Europe figures out that an unsafe condition might exist on an aircraft, they issue one of these, an Airworthiness Directive, or an AD. And this isn't a suggestion, it's a legally binding order. Airlines absolutely must comply with it to keep their planes in the sky. To really see how this all works in the real world, we're going to look at an actual ad that concerns one of the most advanced airliners flying today, the Airbus A350. And this whole story starts not with some big incident, but with a tiny, almost invisible electronic signal, just a little glitch in the engine's data. So specifically, this whole thing applies to the Airbus A350-941, which is powered by these incredible Rolls-Royce Trent XWB engines. But what's really fascinating here is the source of the alert. The very first hint that something was up came from the engine health monitoring system. This system is constantly beaming data from the engines back to engineers on the ground, and it started flagging a recurring alert: fuel metering valve position high. Just a subtle digital clue that something wasn't quite right. All right, so with that little clue, investigators got to work. An electronic alert, it's just a symptom. They needed to find the actual cause. And the hunt for that cause led them deep inside the engine to one single critical component. And here it is. The culprit was a part called the hydromechanical unit, or HMU for short. You can pretty much think of this as the engine's fuel brain. Its entire job is to precisely control the flow of fuel, making sure the engine gets exactly what it needs at the exact moment it needs it. And the investigation found that all those little alerts were pointing right back to this one part. So the technical term for the problem they found is wear-induced stiction. Now, what on earth does that mean? Well, basically, inside that HMU, a tiny little valve was getting sticky. The analogy on the screen is perfect. Just imagine a drawer in your kitchen that, over years of use, just doesn't quite close all the way anymore. That's exactly what was happening here. Normal wear and tear was causing friction and preventing this valve from shutting completely. So a sticky valve that's just a few millimeters wide. That doesn't sound too serious, does it? But in aviation, safety is all about understanding the chain of risk, how one tiny, tiny failure can potentially cascade into something much, much bigger. And here's the first link in that chain. Because that tiny valve wasn't closing all the way, it was causing an unintended fuel leak inside the HMU itself. Fuel was literally seeping past a seal where it was supposed to be completely blocked off. And of course, that internal leak had a direct consequence, a reduction in the fuel flow that was actually being delivered to the engine. The engine wasn't being starved of fuel, but it wasn't getting the precise amount it was asking for. And if the engine doesn't get the right amount of fuel, well, it can't produce the right amount of power. This creates the risk of what's called a thrust shortfall. And what that means is, in a critical moment, like on takeoff when the pilots are demanding maximum power, the engine might not be able to deliver it. And this is the ultimate risk, stated in the very dry, very official language of the safety directive. See, a single engine having a little less thrust is something pilots can handle. But the real danger is if it happened at the exact same time as a failure of the other engine. That scenario, no matter how unlikely, could possibly result in reduced control of the airplane. And in aviation, that is a risk that is simply not acceptable, ever. So with the problem found and the worst-case risk understood, the safety system kicks into high gear. It moves from investigation to action. And the solution is clear, direct, and completely non-negotiable: a mandatory replacement of the part. The directive gets incredibly specific. It identifies the affected parts by their exact part numbers, and it tells airlines they have to replace them with what's called a serviceable part. That can either be a brand new unit straight from the factory or an existing one that has flown for less than a new, much lower flight hour limit.
So for an airline, this whole thing becomes a very clear four-step process. First, they have to go through their entire A350 fleet and find every single engine that has one of these affected HMUs. Then they have to track its operating hours meticulously. Step 3 is to replace that part before it hits the new deadline. And finally, they have to document everything to prove that a certified serviceable part is now in its place.
Now, this part is pretty clever. You can see how the directive actually creates more and more urgency over time. See how the life limit for the part gets shorter and shorter? A part that might be good for another 35,000 hours in 2026, well, by 2027, it has to be replaced by 30,000 hours. And from 2028 on, that drops to 26,500 hours. This staggered approach is really smart because it ensures the entire global fleet gets fixed in a controlled, systematic way without grounding hundreds of planes all at once. Okay, so let's zoom out for a second. We've just gone deep on one technical document about one tiny part on one type of aircraft. But what does it all mean? Why does this single example actually matter so much? This right here is the most crucial point of this entire story. This massive multi-year global engineering effort wasn't triggered by a crash. It wasn't even triggered by an emergency. It was triggered by data. This is the safety system working exactly the way it's supposed to, getting way out ahead of a problem to make sure that a worst-case scenario stays purely theoretical. Think about it. This whole process started with a few bytes of data, just an electronic whisper from an engine flying miles up in the sky. That tiny digital signal was caught, it was analyzed, it was understood, and then it was acted upon, leading to a physical fix on hundreds of aircraft all around the world. It's this perfect, beautiful loop of data leading directly to safety. And that really just leaves us with a final thought. This deep dive into one airworthiness directive, well, it only reveals one layer of these incredibly complex, overlapping systems that are always running in the background. It kind of makes you wonder, doesn't it? What other invisible guardians are out there, watching over every single flight, every single day to make sure you get where you're going safely?